to chapter 4, which focuses on entropy and its relationship to the second law of thermodynamics. And so, in the first law of thermodynamics, we looked at the change in internal energy of the system in its response to the addition of heat, Q, and or work, W. And on the basis of the first law of thermodynamics, we developed the intricacy of the Carnot cycle, which we'll see is a profoundly important contribution to understanding entropy and understanding the second law of thermodynamics. So we turn to the second law and we pay homage to Ludwig Boltzmann, who was the father of statistical mechanics, and statistical mechanics analyzes systems, large numbers of atoms or molecules, and in particular focuses on how energy is distributed amongst and between those molecules and atoms within a large ensemble of atoms and molecules. And remember that we wrote the average energy for a molecule as 3/2 the Boltzmann constant times the temperature. In other words, in a room full of oxygen, nitrogen, carbon dioxide, water, helium, hydrogen, and so on, the energy is partitioned to each of those molecules according to the molecule, not according to their mass. So that equipartition of energy into those molecules is a very important conclusion that comes out of statistical mechanics, and it was developed by Ludwig Boltzmann. But it turns out that Boltzmann had a great deal to say about entropy. And if we look at Boltzmann in slightly greater detail, we notice first of all his tombstone, and on his tombstone is written S, which is entropy, equals K log W. Well, that was 1906. We write that mathematically now as K Boltzmann, in his honor, times the natural log of W. And it turns out that W is the number of microstates in a particular molecular ensemble. And we'll see in just a moment how important microstates are. But it's also a key that we recognize how important his contributions were to statistical mechanics. And in fact, it goes down as one of the great triumphs of the 19th century.